Let's talk about proteins for a second. So when we had something like glucose, the sugar, we said, hey, it's got OH. We had this. Glucose is a reasonably complex structure with lots of shape, and it's about 180 grams per mole. If you have something like hemoglobin, it is roughly 65,000 grams per mole. Molecular formula for sugar was C6H12O6. Molecular formula for hemoglobin, carbon, 2,952, hydrogen, 4,664, oxygen, 832, nitrogen, 812, sulfur, 8, iron, 4. So, needless to say, there's a little bit of a size disparity, and sugars are already complicated enough to draw. How on earth do we show you something as complex as hemoglobin? We cannot write the individual atoms anymore. And that's not just to say leave a few out, like we're leaving carbon and hydrogen out, unless it's on another atom. We can't leave any atoms in. You don't even see most of the molecule. The drawings that we're going to see for proteins give the general shape. Example there. This one. This is hemoglobin. It's actually got 4 parts, pair of dimers, so the blues are the same, the reds are the same. There's 4 sections of it. This is hemoglobin. The little green things are hemes. There's an iron in the center of them. There's some sulfur connecting. You'll notice there's no atoms shown. There's no atoms even hinted. There's just curly shapes. We're going to talk about what those curls represent and how they become useful for showing proteins. So first and foremost, since the consistent part that connects a protein is the amino acid backbone, when we have our nitrogens, double bond oxygen, nitrogen, double bond oxygen, nitrogen, double bond oxygen, and so on and so on and so on. When we have this line, there's R groups coming off, but this continuous amide connection, that is what we call the backbone. That is what the curly drawing is actually showing. Go back to hemoglobin real quick. Those curls, that is following that backbone. All the R groups aren't even being shown here, but they are coming off of those curls. So over here there's some R group, and over here there's some R group. And there's an R group. There's an R group. There's an R group. They're coming off all over the place. We just are not showing them. We'll talk about how we figure out what they are and what they reference, but the idea is they're there. We cannot possibly show 65,000 grams per mole worth of atoms, though. So we need a simplified drawings. For that, there are 4 levels of drawing. Primary, which is a first degree, that is what we drew right here. This is our primary. A primary drawing is just like our very first structure at the start. So if I go back, I look at melanotan-2 here, this is a primary structure. It just is what we think of when we think of organic structures. It is how a chemist would draw things if they were small. Primary quickly gets out of control. And so we rarely actually use the primary. It is just the amino acid list in order. Secondary shows us the local shape. So what does that mean? Well, let's go back up to our examples here. Over here on the right, where we actually show how it kind of links together and curves around, this would be closer to a secondary. So secondary shows you some of the shape, but generally, unless you're a small polypeptide like this, you're going to fall into one of a few classes of shapes. So your secondary has a set of shapes, which let's go look at a few. There are two major types of secondary structure. They are called the alpha helix or the beta pleated sheet, the beta sheet. What happens is, as you grow your chain, as you go from your first amino acid, so number 1 to number 2 to number 3 to number 4 to number 5 to number 6, as you go around connecting them, well, they don't really go in a line. One of the things they can do is they can wrap around something. If you have a cloth or a tie or anything, just hold it in your hand and then start wrapping it up your arm. Imagine you're putting on like a bandage. But don't go around the same spot. Slowly move further up your arm. It just wraps around it. This happens fairly naturally. And so what can occur is that about 3.5 amino acids later, the NH, well, it's fairly polar. That hydrogen is reasonably positive, and earlier in the structure, that oxygen of the carbon oxygen was reasonably negative. So they can hydrogen bond to each other. And so as it starts to curl around, it just tightens or widens until those hydrogen bonds lined up, and there's a best fit at around 3.5 amino acids per turn. As a result, you get plenty of hydrogen bonding, holding the lower level to the upper level. And so as this rolls around, it just kind of sticks to the earlier part of the twist. The R groups come off the sides, whatever those R groups are. There's some coming towards us. It's hard to draw that. But they come off all sides as it goes around. You get about 3.5 of them per rotation. So one level might be, imagine a clock might be like 12, and then 4:30, 7:30 kind of angles. But the next one will be rotated. It might be 10:30, 1:30, and 6, and the next one will be rotated. And so the groups just kind of come off the sides at different positions as they go around. We'll talk about why they coming off at different positions is important, but for now, just the idea that we can attach the amino acid backbone to itself through hydrogen bonding in order to create an alpha helix is part of our secondary. The other way you can do this, instead of adjacent amino acids, like very close amino acids, like I said, 3.5 amino acids later in the chain, alpha helixes are composed of nearby amino acids spiraling on each other. Beta sheets, on the other hand, you'll have a long string of amino acids, you'll have some tail that just kind of wanders off, and you'll have another long string, and those strings happen to line up to create hydrogen bonding between them. This tends to lock them into place. Imagine two pieces of tape that you touch the edges on the long edge. Like, they kind of now are stuck together. And so if you can do this, they'll, if they try to twist or bend up, they change those hydrogen bonds, they pull on them, it resists it. And so depending on what your molecule is, what your amino acid order is, they tend to prefer falling to alpha helixes or to beta sheets. And those different domains are important. As we saw back with hemoglobin, if we go back and look at hemoglobin, alpha helix. There's more alpha helixes. There's more alpha helixes. There's a lot of alpha helix on this molecule. You can have many different alpha helixes. Each alpha helix is part of the secondary structure. When we talk about secondary, we are talking about the local area. So this alpha helix is a secondary structure, and this interaction of the two beta sheets is a secondary structure. There are two separate secondary structures here. That's fine. Secondary structure is just locally what is happening in the chain. Is it curling? Is it making a sheet? Is it doing a loop? That's the idea. So these are our two types of secondary. Let's go back. Local shape. Generally, those are going to be alpha helix or beta sheets. Well, as we saw, there were many alpha helices in hemoglobin, and so we have tertiary. There is tertiary structure. These are one whole amino acid chain in final form. So examples of that, if you had a molecule that had an alpha helix, and then a line, and then some alpha helix, and then another alpha helix, and a line, and another alpha helix. Well, there'd kind of be, there's some secondary here, there's some secondary here, there's some beta sheet going on here. There's a bunch of secondary, but because of how they line up, the beta sheets need multiple strands, alpha helices tend to stick to each other. This overall shape, this is the third degree. Tertiary is the one whole protein chain in all of the different ways that it curls up, looking at the whole thing. Which, well, why do I specify one whole amino acid chain? Go back to our amino acids here. Hemoglobin, you'll notice, we said it's got 4 parts. There's the 2 blues and the 2 reds. It is actually 4 separate proteins. 4 separate things built up, and then another one got nearby and stuck near it, and another one got nearby and stuck to it, and another one. It is made out of 4 separate components, but none of them work on their own. They have to be combined. So when we talk about hemoglobin, it doesn't do you any good to really have one hemoglobin protein. You need the whole hemoglobin complex. And that leads us to our 4th degree, our quaternary structure. Quaternary is multiple separate chains working together. So back to our example over here, if I snag this, and well, it won't let me copy it. Let's bring it down here then. If I had a second one that wrapped around the edges here, so I had a whole new protein, an unattached chain that happened to interact with the first one. Now I have 2 different proteins, 2 different amino acid chains that are sticking to each other, but they are separate chains. This is a quaternary structure. This would be our 4th degree. Some proteins just do what they do on their own, and they only have a tertiary structure. Some proteins, you need multiple to come together and form a complex. So some of them have a 4th degree structure. So in terms of discussing kind of how we talk about the shapes, why we can't draw them like we draw normal molecules, this is some of those components. We're going to dive into more shapes and what they do and how they work to make those large complex shapes. But your primary strand curls into secondary elements, like the alpha helix and beta sheets. Those then twist around and interact with each other to become your overall tertiary protein structure. And if you need several proteins that come together to do the job, whatever that job might be, then you have a quaternary structure. And then just for a few more simplified images of it. I figured this might be kind of nice. You can track on the image here a little bit. I've got a nitrogen, goes to a carbon with an R group, goes to a carbon with a O, that goes to the next one with an R group, goes to a carbon with an O, goes to nitrogen with the next carbon with an R group. They kind of just spiral around. We can follow as it jumps around. So as that backbone rolls around itself, the R groups, you'll notice, are coming off the sides. So I've got an R group here, R group here, R group there. It's a little hard to see that this one's going away in the background, or that this one's coming out at us in the foreground. But the R groups are hanging off this alpha helix. And so those are going to be important in the next talk when we talk about how the different secondary elements interact with each other and the environment around them. But here's a little more detailed, sort of atom level still, where you can see how the secondary elements form from these hydrogen bond interactions.